So we have seen that the Townsend's breakdown criteria is given by this condition: gamma e to the power alpha t is equal to 1. Alpha and gamma, these Townsend's two coefficients, are both dependent on the external electric field E and the pressure of the gas. If the temperature is constant, then the energy distribution will depend only on the value of E by P. And for a particular energy distribution, the probability of an ionization will depend upon the gas density, or rather the pressure. So I can write this relation as alpha by P is a function of E by P. So the Townsend's breakdown mechanism will depend upon not only alpha and gamma, but also the external applied field and the pressure of the gas. Now, how long does it take for the dielectric to break down after I have applied the external electric field? As soon as I apply the electric field, does it proceed to break down? No, a certain time is required for the Townsend mechanism to kick in and this entire condition, the Townsend's breakdown criteria, to be satisfied. So therefore, with respect to the Townsend's mechanism, we can talk about two time lags. So the total time taken can be thought to be comprised of two distinct time lags. One is the statistical time lag Ts, and the other is the formative time lag Tf. What is Ts? Remember, for Townsend mechanisms to even begin, we need at least one primary electron to be present in the electrode gap. And this electron can come from anywhere. It's a stochastic process, and we have no control over when. We cannot predict when this first initiating electron will be available. And therefore, the time required for the first initiating electron to appear in the gap is called the statistical time lag. Of course, we can manipulate the statistical time lag if we do not leave it to chance, but make sure that a primary electron is present in the gap distance. How can we do that? We can do that by irradiation or by injecting a primary electron by some other mechanism into the gap distance. We can reduce the statistical time lag to 0. But after the statistical time lag, when the first initiating electron has appeared, these electrons have to be accelerated from the cathode to the anode. They have to provide ionizing collisions, enough number of ionizing collisions to produce the adequate number of electrons and secondary electrons, etc. So all this will take some time, some finite time. And at the very least, we need the primary electron to reach the cathode, reach the anode from the cathode. At the least, that time is required. The time required for an electron to traverse the entire gap distance, and some of the positive ions at least to traverse the gap distance and reach the cathode and result in secondary processes. So therefore, we can imagine that with a non-zero value of Ts and Tf, there will be a time lag involved in Townsend's breakdown mechanism. However, when we actually look at the breakdown mechanisms in practice, breakdown happening in practice, we find that very often breakdown takes place at a much shorter time than can be explained by the Townsend's mechanism. And something else also happens. We often see that you would have seen lightning. And lightning, we know, never travels in a straight line. The same with these kind of when you have electrode gaps breaking down, and if you can picture the streamers, the pilot leaders, you will see that they follow a kind of zigzag path, very similar to the kind of patterns you see in lightning in the sky. What they never do is you never see a direct strike from one electrode to the other. And Townsend breakdown mechanism does not give me any explanation of why such a path should be visible. So that means there are certain things that Townsend's breakdown criteria cannot explain, which leads us to believe that there might be some processes, some other processes taking place which cannot be explained using Townsend's breakdown mechanism. Maybe there is some other mechanism which is in operation. And that that brings us to the next theory of gas breakdowns in uniform fields, and that is the streamer theory. Let us see what happens in the streamer theory. Let us imagine that there has been a primary electron, initiating electron, and it has begun to move just as before, as you have in the Townsend's mechanism. Collisions are happening in the gap distance, so that as the electron moves, more and more electrons are produced. Now, as electrons are produced, at every point, they will be accelerated very quickly towards the anode. So electrons that are produced anywhere in the gap will quickly move to the anodes. The positive ions are more massive and they will move towards the cathode, but at a much slower rate. So what will happen is, at some point we have a situation where, let's say, most of the collisions are concentrated in this region, and there is a positive charge center. Because the positive ions have not been able to move completely towards the cathode, in this cone there are maybe a reducing number of positive ions. A few have reached, few more trailing here, few more trailing here, most of them located here. Same with the electrons, most of them have already reached the anode, but some are still there and trailing, and they are ahead of the cathode, and this whole thing is towards the cathode. So what I'm saying is, there might be a sufficient number of ionizing collisions at a point within the gap distance, so that there is a charge center, effective charge center here of positive. Ahead of this, there is a negative charge center. Most of the electrons have already reached the anode, some are trailing in this region, and most of the positive ions have not reached the cathode, and they are slowly moving towards the cathode. And it may so happen that the number of these positive or negative charges which are produced in the gas are sufficiently large to distort the applied electric field. If there were no charges, the applied electric field is given by this uniform quantity E naught, which is constant throughout the gap distance. Because of, now if you look at this, there will be a high electric field between this charge center and the cathode, and there will be an even higher field because more electrons and closer to the anode, which is again from the anode to the cathode. So in both these cases, what we see is we have a field intensification. That is, the applied field gets enhanced in front of this space charge, in front of these charges. They get highly enhanced, so the field is much higher, much more, and they get a bit enhanced behind this charge clouds. In between this positive to negative charge, you have an electric field, which is from the charge center to the negative charge center, and it is opposite in direction to the applied external field. So in this region, the field is mitigated. So you have enhancement behind. Now, when you have a large number of charges accumulated in the volume of the dielectric, these are free charges. Whenever you have a large conglomerate concentration of free charge anywhere within this volume of the dielectric, we call that space charge. So we have talked previously about free charges. We have talked about bound charges. The third kind of charge that we will talk about in this course are the space charge. Space charge are free charges which are concentrated in very large quantities somewhere in the volume of the dielectric. So in front of this, this space charge, the effect of the space charge is to enhance the electric field in front of the space charge towards the anode, somewhat enhance the electric field, but not that much, behind the space charge cloud towards the cathode, but reduce the applied electric field inside the space charge region. So what we see is, because of the formation of an avalanche by an initiating electron by Townsend's primary processes, there is a large local electric field enhancement by the ion space charge at the head of the avalanche. And this may lead to the situation where something other than Townsend's mechanism begins to develop within the gas.